The next chapter we will cover is chapter 5. This chapter covers gases, something we talked about a little bit in the first sort of intro chapter. But in this chapter, we'll dig a little bit deeper into what exactly is going on when we talk about a gas. So I've taken the gases chapter and I've sort of made an abridged version, so it's sort of a condensed version that I think covers pretty much everything important. So let's just dig right into it. So the first thing, what is a gas? Okay, so we're all pretty familiar with this. We kind of have a general idea. It's something like, the air we breathe, or maybe helium in a balloon. So we're familiar with a gas, but this chapter will put some more like formal definitions to things, and we'll talk about things maybe you haven't thought about. Okay, and some calculations too. Okay, so gases are composed of particles that are moving randomly and very fast around their containers. Okay, so they're moving randomly and very, very quick. Okay, so they're sort of just bouncing all around. Gas particles move in a straight line until they collide with either the container wall or particle. Okay, so we're going to have a gas particle, and it's going to move in a straight line until it either runs into some sort of barrier, or maybe it runs into like another gas molecule coming the other direction, something like that. Okay, a gaseous atom or molecule exerts force when it collides with a surface or other gaseous particles. Okay, we call this molecular collision, we call this as pressure. Okay, so if you think about when you blow air to a balloon, so what's causing all of that air to push outward? So what's pushing, keeping the balloon, making the balloon blow up, in other words, what's keeping that shape? So what's keeping that shape is the gas pressure. So what exactly is gas pressure? So this is from this first example. Okay, it's from the second example too, but the idea of the balloon staying inflated is from the first example. So if we have all of these gas particles smashing into the face of the balloon or into the wall of the balloon, okay, it's going to push outwards. Okay, it just so happens that things like balloons are elastic. Okay, so they're going to stretch from that pressure. And the more pressure we put, the more they stretch until eventually they can pop. Okay, so how are we going to define this pressure? Okay, so gas pressure is a result of constant movement of the gas molecules and their collisions with the surface all around them. And our formal equation here for pressure, so pressure is the force exerted per unit area by gas molecules as they strike the surfaces around them. So as they strike, that's the kind of what I was saying before, as they strike the surface around them. Okay, so pressure will be defined as force per area, or in other words, force over area. So just as an example, one type of pressure surely we've all experienced is this idea of our eardrums popping. Okay, so we have a small membrane inside of our ear, okay, right here. And we have two pressures. We have a pressure that's sort of inside of our heads and a pressure that's, of course, coming from the outside world. Okay, so we have these two. And generally speaking, one's going to be higher than the other. So when one is higher than the other, it will cause that membrane to flex and push out one way or the other. Okay, and we call that popping. So it could be pushed in or it could be pushed out. So if you've ever been scuba diving, this is something for sure you've experienced. Or if you've ever just gone on a trip to the mountains, you've probably experienced this too. So that popping in your ear is a result of the pressures being unequal. Okay, so that's just an example of the exertion of pressure maybe you've experienced before. Okay, so what about if we have pressure or gases trapped in a container? Okay, so the total pressure of a gas depends on several factors. Okay, so what do we want to talk about the total pressure of a gas? Okay, so the first factor here is the concentration of the gas molecules. Okay, so the higher the concentration of the gas particles, the greater the pressure. Okay, so that kind of makes sense, right? So if I have more of something, it's going to push out more. Okay, then we have the number of gas particles. So this kind of goes back to number 1. So these are they're not exactly the same, but they're sort of similar idea. So if I have more gas particles, so concentration is how much gas particles do I have per so much container, and then the number of gas particles, how many do I have in the container. So they're kind of similar ideas, but of course the higher the concentration and the higher number of gas particles, the more pressure they can exert. Okay, so low density of gas particles results in low pressure. Okay, so if I have some example more like this is going to be low pressure, where I have sort of gas particles sort of sparsely scattered throughout a container. And if I have higher density, so that would be like this other example, then I'm going to have a higher pressure. Okay, so as volume increases, the concentration of the gas particles decreases. Okay, so think about that. If I have like a smaller container versus a bigger container, so I take the same amount of gas and I put it into a larger container, I've increased the volume, so now I essentially have lower density. Okay, so my concentration goes down. Okay, so in turn, I'll then have fewer collisions, so I'll have a lower pressure. Okay, so hopefully this makes sense sort of just intuitively. If I have more gas at higher density, I have higher pressure. If I have lower density of gas, I have lower pressure. Okay, the next factor would be the volume of the container, and that basically affects the concentration and the density of the gas. So if I have a bigger container, it's going to take more gas to put higher pressure in that. Then lastly, the average speed of the gas particles, and this is mainly associated with A, the size of the gas particles, and B, the temperature. Okay, so if I have lighter particles, well, it's sort of a balance because lighter particles move faster, but they have less mass. Heavier particles move slower, but they have more mass. So there's sort of a balance there. But if I have higher temperature, then I have a higher speed, and therefore I have more pressure. Okay, so let's talk about some of just the general properties of a gas. Okay, so the first thing to think about when you think of a gas is you should think of sort of this body that has mostly free space. It's sort of how we talk about the actual atom itself. Okay, and this is something we covered, sort of dabbled on in the first chapter. We said that gases are like our least dense form of matter. That's true. So if you kind of take a look at this example, if this is a sample of a gas, just notice that there's all of this sort of free space where there's nothing actually in there. And then when I actually do have particles, as you see, they're sort of just dispersed within this free space. So first thing it says, there's a lot of free space in a gaseous phase because, as you see, it's our least dense form of matter. Okay, and there really is a lot of free space. Gases can be expanded infinitely. So like before we said, a gas will simply fill the size of a container. So we said it has no fixed volume and no fixed shape. So we know it's just going to keep filling this container. Okay, a gas will occupy a container uniformly and completely. So notice, for instance, with this, I don't have like lots and lots of gas particles on one side. No, they're going to disperse throughout the container pretty much uniformly. Okay, so gases will diffuse and mix rapidly. So if I was to introduce a second gas into this, it would diffuse throughout this gas and they would sort of mix very quickly. Okay, it wouldn't take long since there's very little sort of interaction between the gas particles. Okay, we said that gases are, of course, the most disordered phase of matter. And that's, again, because they don't really have any attraction between each other. So the most that they interact is just to sort of, boom, run into each other. Okay, that's really the most they interact between each other. So really it's a highly disordered form of matter. Whereas in something like a solid or liquid, we do have some interaction between the molecules. Okay, so our ideal gas law. This is something we'll use a lot in this chapter. Okay, so this represents essentially the basic properties of a gas. And they've kind of all been put into one equation. We're going to go through and we're going to break down each part of this equation and sort of see how it fits together. The first one, let's just talk about the equation first. So the equation is here. So PV is equal to nRT. So the P is for pressure, and this is usually given in atmospheres. V is for volume, which will be in liters. T is the temperature in Kelvin. N will be the amount, in other words, the number of moles. And R is our ideal gas constant. And there's a few of these, so you kind of have to be careful. But the one that's generally used if we're just doing ideal gas problems will be this version. So 0.08206 liters atmosphere over kelvins per mole. Okay, so make sure you get to know that. And make sure if you're ever doing a calculation, make sure you check what units you're using. So these units should match those units. Okay, so eventually you'll be able to cancel them out and just be left with the unit that you want. Okay, so how do we measure pressure? Okay, so generally pressure is measured through column height. Okay, so we do this with something like this, for instance. So we have sort of a vacuum tube, like a capillary almost kind of tube. Not quite a capillary tube, but a tube that's been vacuumed out. So it has sort of a closed end, and the other end has been dipped into mercury. Okay, what we can do is we know that we have atmospheric pressure pushing down on this mercury. Okay, and that's causing this mercury to be pushed up into this tube. Okay, and so we take the difference between the surface of the mercury and the height of the column, okay, and that gives us whatever our atmospheric pressure is. So in this case, we know that our normal atmospheric pressure is 760 millimeters of mercury. So millimeters of mercury, why? Because literally we're measuring how high a mercury column is. Okay, so that's where we get the millimeters of mercury. You also see inches of mercury. It's all the same thing, it's just a different unit, but same concept. Okay, so one thing we need to know is that our standard ATM, so 1 ATM, basically what we walk around with, or walk around in. Okay, so 1 ATM is equal to 760 milliliters of mercury, 760 torr, which is 29.9 inches of mercury, and about 34 feet of water. Make sure you can cover up between these units, especially these first two, and then pascals. Make sure you know those for sure. Okay, those are the most commonly used one. The inches of mercury and the feet of water, those really aren't used very much. Generally, inches of mercury will just convert to millimeters of mercury. Okay, but do make sure you know how to go from atmospheres to millimeters of mercury to torr, which are equal, so it's pretty easy. So 1 atmosphere is equal to 760 torr, which is also equal to 760 millimeters of mercury. And make sure you can convert to pascals. Okay, so 1 ATM is 101.325 kilopascals. So no, it's not just pascals, it's kilopascals. Okay, so just make sure you can change between those units. You don't have to worry about how necessarily a barometer works, but make sure you can transfer between the units. Okay, so here's just another breakdown of some units for you. We kind of talked about this already, so I'll just skip forward. Let's take a deeper look at sort of our ideal gas law here. Okay, so the ideal gas law brings together the properties of a gas. So I kind of said that before. So it sort of brings all of those properties together, and sort of unites them in one equation. So it can be derived from experiments and from theory. Okay, so this was several experiments and several theories all kind of put together to give us this one ideal gas law. That's actually very useful. Okay, so we're going to break down each section of this. Okay, so we have our P and our V term. Okay, so this would be under constant number of moles and constant temperature. Okay, and this would be Boyle's law. And we'll talk about this more in just a second. Okay, but it basically tells us that how volume is proportional to 1 over P. Okay, then we have Charles' law section and we have Avogadro's law. So let's take a look at these individually. Okay, so the first one is Boyle's law, and do make sure you know each of these laws individually. Okay, when the properties of amount and temperature are kept constant, then PV is equal to nRT, right? So we're holding N, so N is constant, T is constant, and R is our ideal gas constant. Okay, so we're just modifying P and V. Okay, this means that as the pressure goes up, then the volume must go down in order to maintain that relationship. Okay, and pressure and volume have an inverse relationship. So our example is over here. Okay, so we have the same number of gas particles in each of these. Okay, and we have the same temperature. So the only thing we're going to modify is the pressure and the volume. Okay, so we're modifying pressure using a weight. So here we have a 2 kg weight, and here we have a 1 kg weight. Okay, so the only difference between these two is the size of the weight being placed on top of sort of the chamber. Okay, what happens is, if we have the 1 kg weight, so we have a pressure of 1 atm, so pressure is 1 atm, volume is 1 liter. Okay, so this 1 kg you could kind of think about as representing 1 atm of pressure, or 1 atmosphere of pressure. Okay, so if we double that weight, so we make it a 2 kg weight, okay, we also increase our pressure to 2 atm, but look what happens to our volume. It goes down by half. So we've doubled our pressure. So in order to compensate, our volume has to go down. Okay, so we end up with this inverse relationship. So that means as one goes up, the other has to come down to compensate. And the same is true the other way. Okay, so if you think about doubling the volume, then your pressure actually cuts in half. So it's the same thing. Okay, so you just have to take a look at it and realize that they're inversely proportional, meaning if one goes up, the other has to come down. Okay, so that's assuming we keep the number of moles and the temperature constant. So let's just take a closer look at the experiment. So notice, again, if we double the pressure, the volume decreases by half, and if we increase the volume, if we double the volume, in other words, then the pressure is increased or decreased by half. Okay, the next one is Charles's law. Okay, so if the amount and pressure are held constant, okay, then we can look at V and T. And what we see is that volume and temperature are directly related. Okay, so let's see if I have a close-up of this one. I do. Okay, so remember what we're keeping constant here. So N and P are constant. So we're looking at volume and temperature. Okay, so on the left we have an ice water bath with the balloon with some air inside of it. And on the right we have boiling water, okay, with, again, the same balloon and some gas inside it. So what we see is, if in the cold balloon we have a much smaller volume, and a much lower temperature. Okay, so remember these two things are directly related. So if we then instead take the balloon and put it into the boiling water, now we have a much higher temperature, and notice our volume. So notice this volume size versus this volume size. Okay, so pretty much a dramatic increase when you put it into the boiling water. And the reason that is because the boiling water, so the increased temperature, is giving more energy to those gas particles, and therefore it's able to push out harder against the balloon. Okay, so we're not increasing the number of gas particles, we're not doing anything like that. Okay, but what we have done, so we've raised the temperature, which gives them more energy. More energy gives them more force to push against the balloon. Okay, so these two are directly related. So temperature, temperature and volume are directly related. Okay, the last one, Gay-Lussac's law. Okay, so here we're looking for at pressure and temperature. Okay, where N and V are kept constant. Okay, so again, we have a direct relationship between pressure and temperature. So in other words, if the pressure increases, the temperature also increases. Okay, and for the same reasons as we talked about with volume. So if we increase the temperature, we're putting more energy into those particles, so therefore they have more energy, so they can push out harder. So they're moving faster, so they have more collisions. Okay, and those collisions they do have have more force. Okay, so we end up with a higher pressure. Okay, so this would be why water boils at a lower temperature and high elevations. Okay, so there's less pressure pushing down on the water. Okay, and part of the mechanics of how a kernel of corn pops. So basically, as you raise the temperature, there's more force to push out and break open the popcorn kernel. Last one, Avogadro's law. Okay, so it looks at the relationship between the gas's volume and the amount of the gas when P and T are kept constant. So again, volume and N, or V and N, so volume and number of particles are directly related. Okay, so equal volumes of gases at the same T and P have the same number of gas particles. In other words, as I increase volume, okay, I increase the number of moles, assuming everything else is held constant. Or in other words, you could say it as the amount of the gas increases. So if I increase the number of moles, okay, then I have to increase my volume, assuming everything else is held constant. Probably the better way of looking at it. Let's take a look again at our ideal gas law. So remember, PV is equal to nRT, where P is pressure, V is volume, T is the temperature in Kelvin, N is the number of moles, and again, R is our ideal gas constant. Okay, so here's a question for us to try. So it says, how many moles of N2 is needed to fill a small room that has a volume of 27,000 liters, a pressure of 745 millimeters of mercury, and that's at 25 degrees C. Okay, so I went ahead and gave you your R constant again here. Okay, so see if you can calculate the number of moles. Remember, PV is equal to nRT. So just rearrange that equation to solve for what you need. Okay, plug everything else in, and you should be able to find this answer. Okay, so pause the video and see if you can solve this one. Okay, so let's take a look at this one. So the first thing with a problem like this is let's just go ahead and convert our units. Okay, so we can write our equation that we need. Okay, so remember we're looking at this PV equal to nRT. Okay, and we have our ideal gas constant here. So let's go ahead and put everything into the right units. So the first one we have 27,000 liters. Liters is good, but let's make this 2.7 times 10 to the 1, 2, 3, 4 to the 4th power, just to make it a little easier to handle. Okay, the next one, our temperature. So we need to convert temperature in Celsius, okay, to temperature in Kelvin. So we'll just add 273. Okay, so that gives us about 298. That's not a very good K. So make sure it's in Kelvin. Okay, and the last one, millimeters of mercury. So when I go to atmosphere, so we'll start from 745. Okay, and then remember that in 1 ATM. Oh, I should put that in units here, huh? Let me just start over. Okay, so I have 745 millimeters of mercury. Okay, and remember that in 1 ATM, there's 760 millimeters of mercury. Okay, so this gives about 0.980. Oops. So just under 1 ATM. Okay, so now we should have everything we need to solve this problem. Okay, so we're looking at for the number of moles. Okay, so in other words, we really need to rearrange our equation to give us number of moles. So let's just rewrite our equation. PV is equal to nRT. Okay, so we want N by itself, so let's divide by RT to both sides. Okay, so we end up with N is equal to PV over RT. Okay, we have all our numbers, so I'm going to slide this up. Okay, and now we can just plug everything in. Okay, so our P, we found our pressure is 0.980 atm. Our volume, you know what? I'm going to write this down below because we're going to run out of room if I don't. Okay, so let's just start over down here. So N is equal to PV over RT. Just fix my settings so it doesn't pick up my hand again. Okay, our pressure 0.980 atm. Okay, our volume we said was 2.7 times 10 to the 4th liters. Okay, then we need to put that over R, which remember our gas constant here, 0.08206 liter. Oops, sorry, that's not very, doesn't look very good. Liter ATM over moles Kelvin, or Kelvin moles, doesn't matter which way you write it. Okay, then lastly times our temperature, okay, which we said was 298 K. Okay, now let's check our units real quick. So ATM, I cancel with ATM, liters will cancel with liters, Kelvin will cancel with Kelvin, and we're left with 1 over moles in the denominator. Okay, so remember, anytime you have 1 over something in your denominator, when you flip it back up to the top, it goes on the top. So what we really have left with is, what we're left with is units of moles. Okay, if we go through and do this math, this is pretty simple arithmetic now. Okay, so we've plugged everything in. All I have to do is plug this into our calculator now, and we come up with an answer of 1.1 times 10 to the 3rd moles. We can say, just for clarity, we could say moles of N2. Okay, and that would be our final answer. Okay, so hopefully these are not too tough. And again, I'll post these sheets for you guys on the blackboard, so you don't have to worry about trying to zoom in on your phone or anything like that. Okay, and I do have this typed in for you guys, so we could go over this again very quickly. So the first thing we did was we put everything into the right units. Okay, so we converted our volume. Our volume was already in liters, but we just turned it into scientific notation to make it a little bit easier to deal with. We converted our temperature to Kelvin, put our pressure in atmospheres. Okay, then we just took our ideal gas law, rearranged it to fit what we needed, plugged everything in, okay, and we end up with this number of moles. Okay, so that's how to use the ideal gas equation. Let's take a look at Dalton's law of partial pressures. Okay, so the total pressure in a container equals the summation of the partial pressures of all the gases present in the container. Okay, in other words, whatever pressures of gases we put into a container, the total pressure inside of that container will be equal to the total of all the pressures we put in. Okay, so if we put up at the top here, we put some pressure of gas 1, some pressure of gas 2. Okay, the P total will be equal to P1 plus P2. In other words, just total up the pressures that we put in. Okay, so we could also use this if, for instance, we know the pressure of the total pressure, and we can calculate the pressure of one, we can then use that to calculate the pressure of the other. Okay, so down at the bottom we say Dalton's law expresses mathematically the relationship of all gases present in a mixture to the total pressure in the container. Okay, and to put it into a formula, Dalton's law of partial pressure says that P total is equal to the P of A plus the P of B, and so on and so forth. Okay, so just sum up however many gases you have, just sum up their pressures. Okay, so suppose I give you this equation, or this problem. It says, given the following reaction, what is the total pressure in the flask where the decomposition of hydrogen peroxide H2O2 occurs? Okay, so this is just a simple Dalton's pressure law. Give this one a try, and then we'll go over it together. Okay, so we just need Dalton's law for this one. Okay, so we'll just write out our Dalton law. Remember that our total pressure of gas in the mixture is just P of A plus P of B. Okay, so here we have H2O2, which is a liquid, and it decomposes into vaporous water, or gaseous water, so H2O gas, and oxygen gas. And then we have two partial pressures for these. So therefore our total pressure becomes, our P total is equal to the pressure of H2O plus the pressure of oxygen. Okay, so our P total is equal to 0.031 plus 0.016, just the numbers they gave us up top. Okay, so our total pressure is just 0.0487 atm. So it's just the sum of all the pressures that were inside the flask. Okay, so let's take a look at some different versions of Dalton's law. Okay, so the one we just looked at, we said P total is equal to P of A plus P of B. Okay, but suppose we're looking at a version when the information given states that gas was collected in water. Okay, so we're going to say P total is equal to the P of H2O plus the P of a gas. Okay, the big difference here is that the table of partial pressures for water will be used at that specific temperature. So if you collect a gas over water, or in water, we could say, okay, you're going to need to know, you'll need to know what the temperature is, or you'll just need to know what the pressure of the water is. Okay, but we can look up in the table what the partial pressure of water will be at that specific temperature. Okay, so we can also have, when we only know the moles, or the mole fractions of gases, so you can say the P total is equal to the pressure times the mole fraction of A plus the pressure times the mole fraction of B. Okay, remember that the mole fraction of a gas, okay, so the mole fraction of a gas is defined as XA, okay, is equal to the number of moles of A over number of moles of A plus number of moles of B. In other words, the part of the moles over the total. Okay, so whatever we're interested in looking at, that over the total number of moles, and that gives us a fraction. Okay, so here we have a 1.55 liter flask that contains 1.25 grams of nitrogen and 0.850 grams of oxygen at this temperature of 18 degrees C, and it wants us to determine the partial pressure of each gas and the total pressure in the flask. Okay, so this one's a little more complicated, but give it a try and see what you come up with. One small hint on this one is that you'll need to use the ideal gas law twice to find the pressures, and then from there you can find the total pressure. So just keep that in mind. Okay, so let's take a look at this one. So this one might have been sort of difficult if you didn't quite see how to do it, but once I show you the solution, I think you'll find it so easy. Okay, so there's a couple things we need to do. So the first thing we need to do is we want to find the number of moles of each component. So all they gave us here was the amount of each gas, but they gave us mass. Okay, so let's find the number of moles of each component. Okay, so the first thing we need to do is just turn our masses into moles, okay, by using our molar masses. Okay, so just convert number of grams of nitrogen, number of grams of oxygen, just convert those both into moles. So this was sort of the tricky part. how do you end up finding the partial pressure for each of these just given a mass? Well, since we know a temperature, okay, we know our R constant, we know the number of moles now. Okay, so now we can find our pressure. Okay, so they even told us a volume. So they told us a 1.55 liter flask. So all we have to do then is plug all these numbers into our ideal gas equation. And guess what that gives us? It gives us the partial pressure for each of the gases. Okay, so I won't walk through every step of that. I think you can plug things into the ideal gas equation on your own. But once you do that, you have the partial pressure for each of these. Okay, so then just use your Dalton's law, okay, to add those together to get the total pressure. Okay, and that will give you your P total. So we just literally used ideal gas law because we were given all the information we need. So convert grams to moles, then plug everything in the ideal gas equation, okay, and then just use Dalton's law to find the total pressure. So pretty easy one, I think, once you see it. But honestly, without seeing this one, it might have seemed a little bit difficult because how do you convert grams into pressure? That doesn't really make much sense. But now that you see it, hopefully that clicks a little bit. Okay, so here's another one. So we have a 0.11 gram H2O2, so hydrogen peroxide, decomposes into oxygen and H2O in a 2.5 liter flask at 25 degrees C. We want to know what is the partial pressure for each of the gases in the flask. Okay, give this one a try and let's see what you come up with. Okay, let's take a look at this one. Again, not an overly complicated one, but one that might be a little bit confusing at first. Okay. So we have hydrogen peroxide decomposing into oxygen into water. Okay, so they don't give us an equation here. So the first thing we need to do is write a balanced chemical equation. Okay, and so we just have H2O2, and then an arrow, gives us O2 and H2O. I'll show you that in just a moment. Okay, then we want to calculate the moles of H2O2, and then from that we can calculate the moles of O2, of oxygen, and H2O. Okay, then lastly we can determine the pressures using the ideal gas law. So it's sort of similar to the one we did before. Okay, so first thing we need to do, just write a balanced equation. Okay, so here we have H2O2 decomposing into water and oxygen. Okay, so the only thing we really have to worry about here is balancing out the oxygens here. So we have, if we didn't put our coefficients in, we would have 2 hydrogen, 2 oxygen, and then on our right hand side we have 2 hydrogen and 3 oxygen, so we have to balance it out somehow. So if we put a 2 in front of the H2O, that gives us 4 hydrogen, and then 1, 2, 3, 4 oxygen. So if we just put a 2 in front of hydrogen peroxide, that will be balanced. Okay, so no big deal. Next thing, determine the number of moles of oxygen. Okay, so how are we going to do this? Well, if you remember back to our stoichiometry chapter, okay, so we know how much of our reactants we're putting in. We know our stoichiometric ratio, okay, our molar ratio. So we can just simply first find the number of moles of hydrogen peroxide, okay, and then use stoichiometry. So just take our number of moles of hydrogen peroxide. We see that it's a 1 to 2 relationship. So there's 1 mole of oxygen for every 2 moles of H2O2, which will ultimately give us the moles of oxygen. Okay, I'll go back for a second. Okay, so that will give us the moles of oxygen. From there, we can determine the pressure of oxygen. So if we know the moles, we can use our ideal gas law to determine the pressure. Okay, so just like we did before, plug everything into the ideal gas law, that will give you pressure. So the question just asked us to find the pressure for each gas in the flask. It didn't actually ask us to find the total pressure or anything like that, which we could do. We could just add them together. Okay, so the next step, we want to determine the pressure of water. So we're going to do the same thing. So we know how many moles of H2O2, and we know it's a 2 to 2 relationship, no it's 1-to-1 relationship. Okay, so we have equal number of moles of water and H2O2. Plug again into your ideal gas equation, and then solve for the pressure. Yeah, I know I went through that kind of quickly. I know we've gone through gases pretty quickly, but I feel like this is one of the simpler chapters. Really, this equation is not that robust in terms of the way we're using it, at least in this case. Okay, so basically, all you wanted to do here was get to the number of moles of each gas, and you'd use that by using the stoichiometric ratio. And from there, you could get the number of moles, and from there, you could get the pressure using the ideal gas law. Okay, so we are actually almost finished with this chapter, believe it or not. When I said I condensed it, I was telling you the truth, but we have a little bit more to go. Okay, so the last thing here is kinetic molecular theory. Okay, so this sort of explains some of the behavior of gases. Okay, so the first part is that we assume that gases are consistent of particles, or gases consist of particles, and remember we said they're in constant random motion. Okay, so gases are in motion, and they all have the same kinetic energy. So in a given sample of a gas, they all have the same amount of energy, they all have the same mass, they're at the same temperature, so we're going to assume they have the same kinetic energy. Okay, we said pressure arises from collisions with the container walls, and we said there's no attractive or repulsive forces existing between the gas particles. Okay, so keep in mind this is for ideal gases. So we've used that phrase, ideal gas law. Well, these are ideal gases, so there's no attractive or repulsive forces between the particles. Okay, then that leads us to this. So collisions are considered to be elastic. Okay, in other words, there's no exchange of energy and there's no loss of energy. Okay, and therefore not inelastic, in other words, where you would change energy. So elastic collisions look like this first example here, where we have some, looks like pool balls flying in from the sides. Okay, and they're going to hit each other and they're going to bounce off. And they're not going to transfer any of their energy to the other. So that would be an elastic collision. Whereas an inelastic collision would be something like this, where two objects are coming at each other, and when they hit each other, they sort of stick to each other, and they transfer energy into each other. Okay, so there's no loss or exchange of energy. Again, we're assuming this is ideal condition, so ideal gases. Okay, so there's no interaction whatsoever, aside from collisions, which are elastic collisions. In other words, they don't transfer energy. Okay, so we assume that the actual gas particles themselves essentially have negligible volume. Okay, all gases have the same average kinetic energy. So in other words, any given particle of gas within a sample, as long as they're at the same temperature, they have the same kinetic energy, and that's even independent of their mass. Again, we're talking about ideal gases here. Okay, so we don't really want to put a whole lot of our thought into whether or not they have different energy. We all assume that they have all the same energy. Again, for ideal gases. Okay, and again, it's assumed that the gas particles are in constant motion, and therefore they all have the same kinetic energy. And we'll define kinetic energy as 1/2 the mass times the speed squared. Okay, and we know that as temperature increases, the kinetic energy also increases. Okay, so this slide is just saying that within a sample of gas, the actual molecules will have a range of speed at the same temperature. Okay, so the lower the temperature, the less a range of speeds we have. So in this plot over here, we have relative number of N2 molecules with the indicated velocity and the molecular velocity. Okay, so at 273 K, we have a more narrow distribution, meaning that more of the molecules have this lower velocity. If we increase the temperature, well, now we have a higher possible velocity, and therefore our distribution will be wider, meaning that there's more particles that have low velocity and more particles at high, but most of them have this medium velocity, which is somewhere in the middle. And if we increase the temperature even more, we're going to widen that curve again. Okay, and we have even a bigger distribution. Okay, so don't try to take too much from this. Just understand that any given temperature, our gas particles or our gas molecules have a wide range of velocities, and the lower the temperature, the smaller that range is, because the smaller the possibilities are. Okay, so just keep that in mind. But okay, just kind of remember, with ideal gases, we're kind of assume everything has the same kinetic energy and that kind of thing. Okay, and this leads us to what we call the root mean squared velocity of a gas particle. Okay, this gives you just sort of an idea of the average speed of any gas particle in a given sample. And we calculate this as U, so the root mean squared, okay, is equal to the square root of 3 times R times T over M. Okay, where T is the temperature, just like always. R is our ideal gas constant. This time it's in kilojoules per Kelvin per mole. Okay, so we need a little bit different units since we're talking about energy this time. Okay, and then the big M is just the molar mass. Okay, so it gives you an idea of how fast the average molecule of gas will be traveling at a given temperature. Okay, and it says speed increases with increasing temperature. Okay, and therefore we have an increased kinetic energy. And we say speed decreases with increased molar mass. So this puts both of those things together. So this is more like behaving like a real gas. So if we wanted to start talking about how do gases behave in the real world, we might talk about their root mean squared velocity, where that accounts for the temperature and their actual molar mass. So the only real question I might ask you about this is just, given all of these information, can you calculate root mean squared, which is not a huge ordeal as long as you know that equation. Okay, so this sort of puts together the molar mass of a gas molecule, and then their molecular velocity. Okay, so you see that a lighter gas like oxygen compared to something like, well, let me